Okay. So, hello everyone. Hope you're doing well during this quarantine days. Um, can uh, can everyone mute their microscope, please? Okay. So, hello everyone. Hope you're doing well during this quarantine days. And yeah, so without wasting much time further, let's start with our today's talk on analogy on quantum computing and Q sharp. Briefly, I would like to introduce myself. My name is Jayrang. I am pursuing as a sophomore undergraduate at PDPU, Gandhinagar. Also, you might see I am a Microsoft student partner. And yeah, apart from that, I'm the same person who's been spamming your mailbox since past 2 days. So yeah, let's begin. Um, So yeah, these are going to be the topics of our today's discussion. What is quantum computing? What is quantum tunneling? The entanglement? What is qubit and how to measure it? What is Dirac notation and all its measurements? Superdense coding, a quantum logic gate, Microsoft's QDK, what is Q sharp, and finally the applications of quantum computing. Yeah. So okay. So yes, firstly, our most awaited question is, what is quantum computing? In order to understand what quantum computing is, I think we first need to understand why we need quantum computing. Factorization of large number into its subsequent prime numbers, which can be done using Shor's algorithm, which will be covering into next sessions. Searching through unstructured or unlocalized data. Again, Grover's algorithm can be used to signify that. Furthermore, breaking hash functions. Although actually this is a black hat hacking perspectives, but since it is one of the most trending applications of quantum computing, I had to take it into the consideration. So we will be discussing a brief about these applications on cryptography as well. Simulations of
Isn't black hat hacking is illegal right now?
yeah, it is. Okay. So simulations of quantum systems. This has to do something with the current scenario that is related to COVID-19 and some other biological issues world is currently facing. Apart from that, statistical optimization for machine learning models, one of the best models for data science in today's world, usually runs at a great clock speed and of course the high-end GPUs. But against it, even a single quantum computer can create an exponential decrease in processing time if simulated in the best manner. So, looking at the above examples, you might find that at a certain point, even the largest of supercomputers will fail to answer the iterations. This is why we need a new kind of solution, a quantum solution, perhaps to break the limits of computing and maybe to even explore new horizons like quantum machine learning, quantum cryptography, and etc. So yeah, quantum computing is thus you can say an application as a subject of which one can use the principles of quantum mechanics to encode a certain program and solve the limiting cases of classical computer which our current computers fail to do so. Now you must
Can
be aware
can
yeah.
quantum computers solve unsolvable problems like we cannot solve normally, like not exponential? Those are unsolvable.
Yeah, we can. Definitely we can. But you see, it cannot solve every single question, right? Like if you want to find the value of infinity, you just cannot do it with even quantum computers. Okay, so quantum computer basically reduces the exponential time and the exponential space it requires on classical computers to do. So yes, quantum physics does has its part in solving out some of the things that classical computers are not able to do. Yeah.
Are we going to discuss about quantum supremacy?
No, not right now. We can definitely include it in further sessions if everyone agrees to do. Okay. So yeah. What I was saying was you must be wondering that what this let me just take a pen and highlight it out. Okay. So what is quantum physics, right? So now you must be wondering what this principle of quantum mechanics mean by matter at a quantum level can be in a superposition of multiple classical states, and those many states interfere with each other like waves in a tide pool. Like you can interpret it like within a single qubit there will be millions of different values like 0. 0.1, 0.022, 0.07, floating around and just striking with each other to finally make sense, right? So the state of matter after the measure collapses into one of the classical states, that is either 0 or 1. This means that with every moment of time, there is a corresponding value of a qubit which it holds only for that instant of time. And when we measure the qubit, that is its corresponding value will be assigned to it for the operation, right? This scenario is referred to as quantum entanglement, which we'll be covering in the upcoming slides. Okay, so the next is what is quantum tunneling. Although this topic is a slide related to quantum mechanics more than quantum computing, but still it has the Microsoft QDK that we're about to learn in the next slides does include this concept as well for encoding. Okay, so quantum tunneling is a concept through which subatomic particles existence disappears from one side of a barrier, and at the same instant of time it appears on the other side of the barrier. Let me just say it once more so that you can have a little clear more idea. Quantum tunneling is a concept through which subatomic particles existence disappears from one side of the barrier and is found just at the other side of the barrier, like this.
Teleportation,
Okay.
kind of.
Yeah, you can say that it is a bit of teleportation, but not entirely, because teleportation focuses on bringing the entire matter to one from one side to another side, whereas quantum tunneling just focuses on passing a single qubit from one side to another. Yeah,
Okay.
so you can see the qubit is transferred from one side to another, even though there's a barrier in between. This is how quantum tunneling works. This this you see the small chunk is reflected back. That is because we are not using a pure qubit. What has been seen here is actually a NISQ qubit. NISQ stands for noisy intermediate scale qubit. The current qubit stage at which we are trying to encode all the programmings are the NISQ based qubits and not the pure qubits. Okay, so what is quantum entanglement? One of the principles behind how actually qubit starts to measure. So quantum entanglement is simply a phenomenon through which one can determine the state of another qubit of the same pair, right? Quantum entanglement is simply a phenomenon through which one can determine the state of a single qubit just by looking at the another qubit of the same pair. Like for example, if say I am standing at the starting of the universe with one qubit, and my another friend is standing at the end of the universe with another qubit, but these both qubits belong to a same pair. So let's just say the means of measuring the qubit we are using is the angular spin, the angular spin of the subatomic particle of the qubit. So let's say I have my qubit's angular spin as +1/2. So my friend's qubit will have a -1/2 angular spin. Now, if I change mine, to -1/2, at the same instant of time, my friend will see that its qubit has now the angular spin of +1/2. So you can see that through this mode of communication, we can actually transfer the information we want to send. You can even take the example of the movie Interstellar, the way he ticks the clock, and his daughter, which is apart, can know what he's trying to send, right? Okay. So is what is qubit, right? The idea of the quantum computing starts with the notion of a qubit. Of course, it's the basic building block of quantum computing, and the entire quantum application based solutions
Hi.
that are generated. Uh, can you please mute your microphone? Okay. So the idea of quantum computing starts with the notion of a qubit. It's the most basic building block of quantum computing, and the entire quantum application based solutions that are programmed using the languages of quantum languages like Q sharp and Google's Cirq or Hyperfermion are based on the values of qubits and not the qubits. Qubit at an instant does not possess a value either 0 or 1, but rather at once possesses both the values. That is to say, I mean, there is a superposition of both the values, and the one with higher probability will have the higher rate of getting measured. Like for example, say there is alpha. Just let me write it down. The let's say the probability of 0 is alpha. So if you want to see the current state of qubit, it will be something like alpha into the current state of 0 plus beta into current state of 1. So this is how a qubit can be measured. This, this is not the way to be measured. This is just the current state. This is how a current state of qubit is defined by. Okay, so let me just read this out. And yeah, cool. So it can be written as, if 0 is considered as the column matrix of 1 and 0, and the state of 1 is considered as the column matrix of 0 and 1, the current state, that is the psi, the current state of the qubit we are seeing, can be written as alpha times current state of 0 plus beta times current state of 1. And if you can do the scalar addition, you can see that it is nothing but alpha and beta. That is when we multiply 0, this, just a minute, let me take the black here. Okay, when we take this and multiply it with alpha, we can see that here there will be alpha multiplied and it will still remain 0. And when we multiply beta with the current state of 1, we will find beta here. So adding the both the column the column matrices, we can see that alpha and beta is the current state. This signifies the current state of qubit and not the value of qubit itself. Okay, so what is measurement and how it is different from the current state? Measurement, one of the most important topics, without which one cannot capture the value of a qubit, as I said, and also without which one cannot program any set of processes or simulations on a classical computer. If we don't have a quantum computer, we obviously try to simulate it on a classical computer, but without measurement, yes, we cannot process any set of instructions on a classical computer. In order to understand this, we need to understand the higher order matrix concepts and the Bayesian techniques, but since it will get a little too more technical, I'm just skipping that part and just giving a brief idea of how that works. Okay, so yes, when a qubit at a current, just let me take the black pen again. Okay, when the current qubit state is passed through a measurement device, it will produce either 0 or 1 based on the measurement technique. Let's say the example that I just gave, angular spin is what my measurement device is, and the current qubit I'm passing through has an angular spin of +1/2. and have encoded that if there is +1 of passing through, that is above 0, encode it as 1. And if it's otherwise, that is -1/2, encode it as 0. So that is how a qubit is measured after quantum state has collapsed, and the quantum state collapse only through a measurement device. So that is how from the current state of qubit we can measure what can be the classical value. After getting this classical value, we are now ready to program it on either a quantum computer or its simulation on a classical computer. Okay, and one more thing. Here you have seen that when a qubit is when a qubit given by the quantum state vector alpha and beta is measured, we obtain the probability outcome 0 with the probability of alpha square. As I said, alpha is the amount, the proportion of which 0 is defined in the current state of a qubit, and alpha square, sorry, the module of alpha square is the probability that after collapsing, it will change to 0. And the same goes for 1 with the probability of beta square. Again, beta stands as the proportionate amount of the current state of qubit, and beta square, sorry, the module of beta square stands the probability with which after collapsing the outcome will be 1. Okay, so after the measurement, what now? Qubit goes from being a superposition state where it contains the value of both the proportionate amount, as I said, that is the alpha times probability of 0 plus beta times probability of 1. Excuse me. Uh, in a proportionate amount of alpha times current state of 0 plus beta times current state of 1 into one of the classical values, that is 0 on 1. And with that, as we have been already familiarized with the notion of quantum entanglement, the corresponding value of another qubit within the same pair will be known automatically. So let's say I have a pair of qubit that I am passing, and after measuring one of the qubit, let's say that this is 0. This both qubit belongs to the same pair. Sorry, let's say Q2 and Q1. These both qubits belong to the same pair. And if I am able to measure one of the qubit and the outcome is 0, I can automatically say that this another qubit will have the value 1. That is how quantum entanglement works. And with the same property, we are going to infuse multiple qubits into our programming simulations, and we'll tend to use quantum entanglement as a concept through which we will measure the current state of the qubit and use it for manipulating our quantum algorithms. Okay, just let me erase it once. Okay. Okay. So yes. Harnessing the quantum attributes has been the pursuit of multiple decades of quantum algorithm research, and there are many innovative techniques that have been found that can solve problems in a fraction of the time that it takes to solve classically. Just before someone mentioned, can it solve the exponential time taking algorithms on a classical computer? Yes, it can definitely, but not all the set of algorithms. There are some things, some mathematical terms, some notions that can't still be defined even with quantum computers. And the technology that can measure that kind of algorithms, that kind of notions, that kind of values are just not into market yet. And if there is, I am not aware about it. Pardon me for that. And yeah, so that's it. Next is what is Dirac notation, the bracket notation. So now that we have seen how actually a qubit works and which set of principle it follows, let's now quickly see what are the standard notations used for expressing a qubit and its operations. Firstly, let me tell you what the tensor product is. So a tensor product is basically an outer product of two different vector spaces, with the resulting vector again being a new vector space which follows the bilinear composition. That is, it follows all the three binomial conditions. Let me rephrase it. Tensor product is basically an outer product of two different vector spaces, with the resulting vector again being a newer vector space which follows the bilinear composition. That is, follows all the three binomial conditions. Now consider that the mathematical equations of classical computers are being used in order to simulate the equations of quantum computing. So can you imagine that we are using the equations of classical computing and trying to manipulate the quantum computing algorithms? Don't you think that it will be much more disastrous, because the current notations we are using in classical computing, like the Greek alphabets and all, are already heavy enough when we try to incorporate it in quantum physics? And here we are talking about quantum computing, a step ahead of quantum mechanics and quantum physics. So equations will be much more than just disastrous word. So yes, you definitely cannot encode it within a classical computers. I mean, on a simulation of quantum simulation of a classical computer, or either quantum computer. Now, in order to overcome this drawback, the inculcation of Dirac notation was made as a standard notation for quantum computing, in order to simplify the forms of equation by using the concepts of quantum mechanics. So yes, Dirac notation follows the principles of quantum mechanics in order to manipulate the all the notations, and makes it easier to encode as well as makes it easier to understand by just have a look at it. Okay. Furthermore, Dirac notation solves this issue by presenting a new language to fit the precise needs of quantum mechanics. Definitely. Again, here we have a newer word. You can see that bracket, right? Bracket. Let me just, yes, this bracket. So the bracket are the notations symbolizing the quantum state. Now you must be wondering that I have written this 0 and this 1. What are they? Well, they are a part of bracket notations. Bracket are the notation symbolizing the quantum state, that is, of course, the value of a qubit at an instant of time. Bray signifies this, on this word, this Bray signifies a linear function that maps a vector space to the complex numbers. That is, it maps a normal Hermitian vector space to a complex numbers. And this cat, specifically this cat, are just the vectors, the ordinary vectors of the Hermitian vector space. So this means that these vectors, these ordinary Hermitian vectors, are then applied to this linear mapping function that takes and converts the ordinary Hermitian space vector to complex set of numbers, because in quantum computing we cannot use classical numbers like 0, 1, and so there are always complex numbers that we have to manipulate in order to compute and encode the entire infrastructure of algorithms of quantum computing. Yeah, so yeah, I have also written that as an example of Dirac notation, consider the bracket, which is the inner product between 0 and 1. So yes, this 0 and 1 doesn't necessarily mean that 0 is any kind of function and this 1 stands for any kind of vector. It just means that there is a bilinear state, that is, there is a function incorporating 1, and there is also the same function incorporating 1 as its another qubit. So with that, multiplying this, or we can say just multiplication of the function, we are here with 0 and 1. You can say that it's bi-qubit manipulations we can use to implement in our quantum algorithms. Say we are needing not a single qubit, but we need 2 pairs of qubits. That is a total of 4 qubits in order to manipulate the information we want to send via the quantum algorithm. We will be needing 2 qubits, and for that this notation is helpful. This 1 means that we're using 1. quantum state, and this means we are using another quantum state, but you can see that this both quantum states belong to a single qubit. Pardon my handwritings, I am just using my mouse for that. So yeah, okay, so yeah, just let me erase it once.
Uh,
Okay,
I
so
have a question on the previous slide.
yeah,
You said entangled state. In entangled state, if one qubit is 1, then the other is 0, right?
yeah,
Can't they have same state, like 1 1 or 0 0?
they definitely can have, but the measurement that we are using cannot allow those kind of manipulations. You can definitely have 0 0 1 1 as the quantum entangled state, but again, when you measure it, you have to always give it the value either 0 or 1. So after measuring, it will be here either 0 or 1, but it will never be 0 0 or 1 1.
Okay.
Yeah, thank you. Okay, so yeah, here I've written that this 0, right? So this 0 has its factor 1 and 0 as stated earlier, and this 1 has the column vector of 0 and 1, right? So you guys can see how can I write this column vector into this row vector. What I've done here is basically took a transpose. Why transpose? Because this 0 is not written likewise. That is, if I write, just let me rub it once again to give a clear idea. Okay, so yeah, remove this all outside. Okay, so yeah, if I write this one, it means 0 and 1. If I write 0 quantum state, then it stands for 1 0. But when I'm using a bilinear function, that is here I'm using 2 qubits, I have to inverse the state of any one of the bits, like say this 0, and this will lead to transpose of the current state. That will lead me to 1 and 0. So now I can multiply this both, that is 0 and 1, and that will lead me to 1 0 and 0 1. After multiplication, as you can clearly see, the state, the overall density, the overall averageness is equal to 0, which means we are currently working with a balanced state. There is no unstable qubits floating around in the entire system. And you have to always make sure that the current state, the current average always remains 0. That way we can ensure that our current system is working functionally and there is no harm or no alerting mechanisms that will be used further, right? Okay, next is continued. Okay, so here I have written psi and phi vectors. Okay, so let me just give it a brief of it. So let's consider this psi is a vector representing the current quantum state. Let me write it here. The current quantum state is defined by this psi vector, and this phi vector represents the current state with respect to 1. That is, it doesn't matter what this state is holding the value, all it sees is whether the incoming qubit has the probability of 1 or not, the higher probability of being 1 or not. So then we can say that the probability of measuring the state of psi with respect to phi has the probability given by phi modulo psi whole square. Again, let me repeat it. Um, the probability of measuring the given state psi, that is with respect to the current state. Sorry, I think I just messed it up. Okay, just let me reset. Yeah. So we can say that the probability of measuring the state of psi with respect to the phi stands for the probability of being 1, and psi stands for the current state. We don't know whether it's 0 or it's 1. So when we apply this, the probability that we acquire is mentioned by phi, that is the state we need to be 1, and phi the current state and the whole square. This gives us the probability. Again, you would have seen that mod of alpha square stands for the probability of 0, and beta square stands for the probability of 1. In the same way, when we have a current state and we want to define whether it's going to be 1 or not, we can write this notation of psi with respect to phi modulo square. Okay, so again, let me just drop it. Okay. Okay. Then just let me just. So you guys have already seen this both matrix I have stated. What is Pauli's measurement? Imagine that we have an n qubit quantum state. That is, let's say I have a 1 qubit quantum state. Then the measuring of 1 qubit, that is either 0 or 1, immediately rules out to half of the n square possibilities that the state could be in. Now you would be wondering how the n square probabilities. Well, let's say I am having a probability of 0.33. All I have to do is either give the value 0 or 1. I don't want 0.5, I don't want 0.075, I don't want 0.0001. All I want is either 0 or 1. So that leads me to dividing all of the possibilities that are in between 0 and 1 and just keeping the possibilities either 0 or 1, right? The measurement projects the quantum state onto one of these two half spaces. Half space, again, I have denoted the quantum state of 0 as this matrix, right? So this matrix stands as a half vector space. Half meaning there is a single 0 here and there's a single 1 here. If I have this 1 1 or 1 2, it means that I have a full vector space, a full vector column space. But here 1 and 0 is written, which means that I have a vector half space of the probability of the quantum state 0 and the other half probability quantum state being being this. Okay, so as you guys know, the Q sharp, the most as we are going to work with Q sharp, the most common kind of measurements we will likely to be run into are the Pauli's measurement. What are these Pauli's measurement? They generalize the computational basis vectors and includes all the parameters required to compute the qubits and measure them and then pass it on to quantum algorithms. All of these things are withstand single-handedly by Pauli's measurement. Now, what is this Pauli's measurement? Right? Okay. So, just a minute. Let me erase it once again. Okay, so as I have written here, measurement takes a quantum state and projects it into one of the base vectors, that is either quantum state of 0 or the quantum state of 1, with a likelihood equal to the square of the vector's depth, the distance along the base vector. We have already seen that the likelihood stands here for the probability, and the probability that stands for, let's say, the 0 quantum state is the alpha square, where the 0 vector stands for the half base vector 1 and 0, right? Okay. Again, just pardon me for this. Cool. This is a stochastic non-reversible operation, as it sets the quantum state equal to the base vector that represents the measured state. That is, the state collapsed to a definite single value. Why and how, or even if this is so, this is called the measurement problem. The thing is, there's a drawback with Pauli's measurement. That is, if let's say I have probability of zero vector state, the zero vector quantum state being 0.001, right? So you can see that the error here leads to be too small. Just let me write it small. Okay. When I pass it through Pauli's measurement, what it does is basically it either measures it at 0 or 1. But since there is this 1, it's not the exact 0. I will always have some kind of error, and that's why I'll be having a some value, just a small, very little proportionate amount of 1 as an output, but mostly it will be considering 99.999% of 0 and 0.0001% of 1. Again, it's not the perfect 0, neither is the perfect 1. So while manipulating it, we have to always make sure that this thing always remains close enough to 100, right? I know that this 99.999 is very much near to 100%, but still it cannot manipulate with this. Any qubit cannot be interpreted as 0 just because it has 99.99% probability of being 0, right? It has to always be 100% 0 or 0% 0. It cannot remain 99.99 or it cannot remain even 0.001%. It has to be always and always either 100% or 0% because we are dealing with the quantum states. Quantum states already are a very, very minute components, and when we want to manipulate them, we have to always make sure that there is either zero error or there is no error at all. Okay, cool. So yeah, we can go further. And now, most importantly, what is a quantum logic gate? In the quantum circuit model of computation, a quantum logic gate, or simply a quantum gate, is a basic quantum circuit operating on just a small number of qubits. If we are dealing with simulation on a classical computer, rest it's fine. If you have a quantum computer at home, you can use thousands of qubits at a single time to process out. But if you are using a classical computer and you are simulating qubits, you have to make sure that you use let's say just at max 4 or 5 maximum qubits. Using the multiple qubits will lead into overflowing the data state that have been encoded on these quantum programming languages like Q Sharp or Cirq or even Hyperfermion. Because achieving quantum supremacy is a different thing, and using it for manipulating the quantum algorithm is a whole different thing. Okay, so yeah, so as you can see, yeah, in this table, what basically does is it uses the corresponding matrix. Just let me take pen again. So what it basically does is it takes the, let's say I'm using the Pauli X gate and I'm passing my qubit from here. So what it does is it basically does Bayesian base vector multiplication based on the those three bilinear composition that I have previously mentioned, and finds an outer product of the let's say this qubit has an entangled quantum state of 0, so this will be 1 and 0, and this will be an outer product of this gate. This gate what basically does is it takes this matrix here mentioned and it applies an outer product from the incoming quantum state, and the output will be the outer product of this both matrix, right? Okay. So yeah, it uses the corresponding matrix of the gate and takes the current qubit and finds a tensor product. Again, the tensor product has been mentioned in the previous slides. You can recall what I just told about tensor product. Basically, you press the tensor product on the qubit. Just let me write it in simple terms here again. Okay, so the gate, come on. So the gate is X, the Pauli X gate. This is the tensor product, and this is the incoming qubit. So the output will be another entangled state, or you can say the measured entangled state that will give either 0 or 1, right? Okay, so that's how basically a quantum logic gate works. Furthermore, what is a superdense coding? Though this topic is slightly more related to quantum information, but I thought I should cover it since it's basic and it's really interesting. So in quantum information theory, superdense coding is a kind of a communication protocol that can transmit two classical bits of information using a single qubit, under the assumption that both the entities have already a pre-sharing entangled state, which this from this line, under the assumption that both the entities have been already pre-sharing an entangled state. As I mentioned earlier, the quantum entanglement is the principle governing here into superdense coding, through which a pair of qubits already knows the entangled state of the another qubit, and that way they can either decide whether to be 0 0, or to be 0 1, or to be 1 0, or to be 1 1. Okay, so yes, this is a diagram. Let's just say that we have um, we have a pair of qubit whose both value are currently 0. The unmeasured value is 0, not the measured value, right? Okay, so I'm passing it through one of the Pauli's gate. Then the new state that I have found right here, I'm just adding it with the current state. So this current state, let's say this value will be incorporating 1. So this, either if it's 0 or it's 1, it will basically have 1 on its image, right? So it will be directly passed here, and the y will have the value 1. Now this one state will again go here, and this are the same. Sometime later, some picked qubits, let's say that this qubit has the value 0, and let's say this qubit has the value 1. So now what happens here is it's actually 1 incoming here, and the 1 is added over here. So at this point the value will again be 1, but here I am having a 0, and that is put over a Pauli's another gate, Pauli Z gate. So incoming here is 0, incoming here is 1, and then it is applied as matrix 0 1 with a tensor product of Pauli Z. I mean, just let me read Z, the Z gate, right? That will lead to an output of 0, a compulsion 0 here. So this 0 will again be forwarded here. After passing this 0, now I am again having a control of H. This H gate is similar to this H gate, right? So when I was passing 0 here, I was getting 1 here, right? The same way I'll get 1 here. This way, you can see that even if we didn't know in what kind of entangled state this qubit have with respect to this qubit, they automatically come outside with the measured quantity of 1 1. That means that in classical qubits, if I don't have the information that whether it is 1 or whether it is 0 or 1, I cannot pass it through this gate. This gate will manipulate it wrongly, and the output will be either discarded or some random values, because qubits classical bits never know the state of the another bit of the same pair, whereas qubits of the same pair can share an entangled state and can know what value will be generated of its pairing qubit. So that way, that is the how a superdense coding actually works. Okay. So just a brief example. Let's say an entity 1 wants to send two classical bits of information that relies on either 0, 0, 0, 1, 1, 0 or 1, 1 to entity 2 using qubits instead of classical bits. To do this, an entangled state, that is a Bell state. Bell state again is a common notion for an entangled state. Okay, again just let me get right. Yeah. Bell state again is a simple notion of an entangled state. It's prepared using a Bell circuit or gate by J. J, who is J? J is a third person who is manipulating the qubits in order to receive and send the incoming and the outgoing qubits. J then sends one of these qubits in the Bell state to entity 1 and the other to entity 2. So let's say I want to create a communication between entity 1 and entity 2. What I am doing is sharing two qubits of the same pair, one to each entity. Once entity 1 obtains a qubit in the entangled state, it applies it to a certain quantum gate to its own qubit depending on the 2-bit messages that either the sender wants to send 00, 01, 10 or 11. This message will then be already and automatically known to entity 2 using the concept of quantum entanglement, which is referred to as here. This entangled qubit is then sent to entity 2, whose after retrieval the classical 2-bit message. Make sure that the only message that the entity 1 wants to send is received by entity 2. So let's say here you can say that I want to, this is Jai, this is entity 1 and this is entity 2. What I'm doing is sending one qubit to him and another qubit to her. The entity 1 basically applies some sort of gating techniques, let's say Pauli X gate, and then sends this new qubit to this one. Let's have send him 0 and 0, and I just want to make sure that they communicate 0 and 0. This one qubit is already with entity 2, which is 0. Entity 2 doesn't know that what is the value of this another qubit, and it is only known by entity 1, and entity 1 knows that this value, the value of the another qubit sent to entity 2 is 0. So he knows that the message that will be sent to entity 2 must be 0, 0. What it does is basically uses the Pauli X gate in such a way, in such manipulated way, that it will only send 0 and the corresponding quantum entangled state will be sending it to entity 2. Entity 2, let's say here, receives 1. What entity 2 will do? Basically, it will use the same gate that has been used and will decode it as 0. That way, without knowing the value of the another qubit, you can actually send and verify and authenticate that the information that's sent is the original one sent from entity 1 and not a faster one. Okay, so we are mostly done with the quantum terminologies, and let's just move to the Microsoft's quantum development kit. Okay, so Microsoft QDK is basically Microsoft's venture of quantum computing. They always try to make a perfect QDK model. The governing hardware used for QDK follows these 3 set of rules. Building a quantum computer using reliable, scalable, and fault-tolerant topological qubits. Again, the topological qubits, a newer term. Topological qubits are the type of qubits that are used for storing and manipulating the quantum information, the one which I've stated in the earlier slide, that is the superdense coding. That is in those kind of superdense coding mechanisms, we use the topological qubits for quantum manipulations. Here, these topological qubits are in turn dependent on exotic quasi-particles called anyons. Again, it's getting a little more theoretical physics, but let me just give it a brief. These anyons, they lay emphasis on key properties like how to define an anyon, will they help protecting the encoded message, will they not, will they enable the actual processing of quantum information from short distance range to long distance range, would they not, and all of those things are covered in the topological qubit section, in specifically under the anyon sections. Anyons again are the quasi-state exotic particles, subatomic particles. Yeah, so that's pretty much it. Engineering a unit cryogenic control plane with low power and heat dissipation. The control plane, the cryogenic control plane, that is basically manipulating the very low amount of temperatures, like almost 10 to 0 Kelvin sort of thing. At that very level, we have to make sure that the power used is very less, and also the heat dissipated is 10 to 0, because yeah, I think you definitely know that quantum computers never work on normal room temperature. They, because of their high processing power, they tend to steam off really fast, and in order to separate that heat from the actual processing power, we have to use these cryogenic control planes that make sure to use more and more power and waste less amount of it. And the third is developing a complete software stack to enable programming to the quantum computer and controlling the system at scale. Basically, the Q-sharp language and the QDK, right? Okay, so thus the open source quantum development kit has been introduced to make the quantum programming and algorithm development more accessible. The working of quantum development kit. The applications that we will be developing with QDK are basically divided into two portions. The first one being the quantum algorithm written in the Q-sharp language, and the another one being a host program that has the main work of um, just calling the quantum algorithm, giving it the inputs, manipulating through the entire quantum algorithm, and just taking back the outputs, and um, basically show how the simulation actually works and whether it provides you the results, the expected results you need or you not. Yeah, so the host program is basically written in programming languages either Python or C sharp, and there are no extensions for any other languages, either for C, C++, Java, and the other languages. There is
Yeah,
no
I have a
API.
question.
Yeah.
Yeah, are there any quantum computer consoles which through which we can implement or we could try a hands-on experience on quantum computing?
Not under my watch. I don't know that if anyone is providing the quantum computers. I mean, either Google or the Microsoft.
Like
I don't think that they're
the
providing.
picture and the name of the person who posted everything.
Sorry. Can you repeat, please? Okay. Cool. So I guess I'll move further. Okay.
Hello.
So Microsoft. Yes. Okay. Microsoft's high-level programming language, that is Q Sharp, addresses the challenges of quantum computing and blah blah blah. Yes, the most important one, the Q Sharp compiler. It is integrated into a software stack, basically stack that tends to divide the entire quantum algorithm into chunks of data, chunks of operations, and a single operation is passed alongside a single thread, and the other operations are likewise passed along different threads, and all of these operations work on parallelly. Like say if you have a classical computer and you, yeah, sorry. Okay. Yeah, so the Q-sharp language basically divides the entire piece of algorithm into substitute chunks and executes all of these chunks parallelly in order to fully utilize the processing power of the CPU and simulate the required inference, and gives the user with the output whether the expected out is 0 or it's 1. Okay, so yeah, up to a certain scale, quantum computing can be simulated on a classical computer, as I mentioned it earlier. So yes, these are the steps. Choose a location for application, create a file named Bell. This doesn't necessarily have to be Bell. It can be any name, but just make sure that you give the extension of .qs, because this is the file that contains a Q# code, and this host.py will basically be a Python or a C# code that calls this .qs file and implements all the operations written inside it. Okay. So the Python host application is again divided into 3 subsequent parts. In the illustration that we are going to be covered, the count value is to be fixed at 1000, and the initial value is the initial keyword is the initial value of the qubit that we are passing. The quantum algorithm, by calling the simulate method, as the simulate method will basically incorporate all the operations that are written under Q# language, and will operate all of these operations written inside simulate inside a simulate operation, and run all these operation parallelly. This is just let me reframe it. All the operations written inside simulate method will be running parallelly instead of running piecewise. Processing the result of the operation. In this example, rest receives the result of the operation. Yeah, so these are basically one of the example that we will be covering soon. Cool. So yes, just let's get to coding in just a minute. Okay. And just let me project. Okay. So yeah. Let me just create a new file, a Q# file basically. Okay, so let's write our first, let's say, a hello world program. All we wanted to do is basically just write the message of hello world, and for that, in Q# language, any function is defined by the keyword operation. Inside this, sorry, first you have to name the operation. Let's say I'm naming it as hello world. Inside this parenthesis, you have to pass any number of variables that you want to use. Let's just say that we don't want to use any parameter as of now, so let's just keep it empty. Then you have to pass the keyword, the return type of keyword that you want from this operation. As of now, I just don't want anything, so unit is the keyword you will be using, and if you want to return something, you have to write instead of unit result. Let's say you are just adding two numbers and taking back the added number. Let's say you are giving 2 and 3 as inputs and 5 as the output, so this 5 will be written only if you write the result keyword, and if you write the unit keyword, you will not be able to return the value. So yeah, just as of now, keep it unit. And yeah, so this is our first operation, and inside this, let's say we want to return hello world string. So message, inside that we have to write hello world, and I'll run it. Meanwhile, it generate either it's working or not. I have been given a comment that are you creating an object? Yeah, you can. No, sorry, it's not an object. It's just a random function. Object will be created in a while. I'll show how an object works, but this is just an operation. Okay, so yeah. So you can see that hello world operation has been successfully created, right? So this means that this manipulated operation is now ready to be deployed. And how I can sorry. Okay, so now that I have created an operation, how can I basically output it? I want this hello world message to be printed. So for that, I write simulate this operation and the name of the operation, hello world. See here, you can see that hello world has been printed, right? So now let's just say I want to pass a name and I want it to be printed, right? Basically an object that takes the string as an input and outputs the name. So let's just say that I'm giving it the variable name, and the type, the data type is string. So now what I have to do here is add a $sign for adding a variable name, and here curly braces for the name entered, right? Okay, so yeah, I think it's ready to go.
Top the wall.
Right. Okay, then just keep it here. Now I'm passing the name that
I just wanted to make something.
Yeah. Sorry. Okay, we shall continue. Okay. Let's say I want to print my name. I'm not able to hear
Is
you
there
out clearly. Okay, so
is there
this
any
operation. Sorry.
open the chat box?
Yeah, just a minute. Okay. So someone just said here this link, quick quantum circuit simulator. Let's just see what is this thing. I'm sorry. What is this? Can anyone tell me? Um, uh, Geek Shambhu, can you tell me what this link stands for? Because to be honest, I'm not. I've never seen this. Yeah.
I think so. Geek Sambu has left the conversation.
Oh, okay. I think we shall continue.
Yeah, he left.
Okay, so let's just say that I'm not passing any string here. I want to print the name, my name, that is Jai. Then I have basically created the operation Jai, and I'm not passing any kind of variables because I don't need one. Now what I wanted to do is take this hello world operation, use this hello world operation, and to print the name Jai, right? So here you can see that I have passed a variable that is string. So what I will write here is go to hello world and pass the name Jai, right? So the J is already created. Now you can see that why only J, not hello world, because I have not tried that hello J, neither J. Good. What I've done here is basically created an operation, and this operation name is J, right? So this J stands for the operation name. The operation is ready to be manipulated. Now I'll actually run this J function. Yeah. So here you can see that hello J, right? So this simulate J will now run this operation and not use this operation. This hello world, that is this operation, will be used. The hello name, this hello will be of course it's the ordinary string. This name keyword is the string,
Hello,
and
Jay.
the string that I passed. Yeah.
Why this round brackets are shown in the output?
Okay, that's because I didn't send anything. Yeah, I've written unit, and as I said earlier, that if you wanted to return some kind of result, right? So you have to write result here. That's because I've written unit here, and still I'm messaging here, but I am passing the variable keyword here. Getting
Okay,
my
thanks.
point?
Yeah.
Okay, cool. So with that, I think we can write our first code to find the entangled state of a single qubit. Okay, so you might be knowing that we write import keyword in Python in order to use some kind of APIs or any libraries. In Q#, we write open keyword, and here I'm taking Microsoft.quantum.math, library. So my operation will be to prepare a random keyword. Let's just say message. Okay, and the variable that I'm passing into it is, let me just say q is the word, and qubit here is the data type. And yeah, I don't want to return anything, so let's just keep it unit. Let my choice, let again is the keyword used for declaring variable that can be, I mean, not a static variable. You can change the value of choice at any instant of time you want. So for that we have written let here. All right, so let's just say my choice this time as a random integer value into that is either 0 or 1. Okay, so now if choice is equal to 0, then message we have prepared a negative, or let's just say keep it negative, entangle state, else message prepared a positive state. Yeah, so now we've defined a function that will take the choice, any random choice, and prepare the entangle state, but we haven't defined any kind of operation that actually measures the qubit, right? So let's just define one. If it's the negative entangle state, that mean set minus. Let's just keep it. Set minus is the function I'm using to prepare the negative entangled quantum state. And if it's positive, definitely it's going to be set plus, and the qubit is what I'm passing here as an operator. Now let's just define our two operations. Firstly, operation set minus. Okay, so what's incoming here is again the qubit. Okay, sorry, I just forgot to return that unit. Okay, cool. Now the most simple operation that you can use to manipulate a pair of qubit is by using reset gate. Firstly, you have to always use the reset gate so that it can firstly define the incoming qubit to a random state. Sorry, not the random state, but an equal state. Like say if, and one qubit has the value 0.479 and another has the value. So what we'll be doing is that the reset qubit keyword will basically give both the qubit value of 0.5. That way we will have a base state to start the measurement on, and we can finally separate it either 0 or 1. Let's see how. Okay, so reset is the keyword I am using to manipulate the qubit, and then since it's the minus, I want to firstly pass it through a Pauli X gate and then Pauli H gate in order to measure. Pauli H gate is the one always used when you want to either pass through the entire quantum algorithm, or you want to finally get the value either 0 or 1. At that very stage, you have to use the H. The Pauli H gate basically yields either 0 or 1. The next function will be set plus q and the qubit. Unit. Then again reset the qubit, and since it's plus and I don't want to change the set, so say yes, definitely qubit portion. Yeah, I think okay, so this program that I've written here, basically what it's doing is it takes any random qubit, no sorry, the input qubit, creates any random integer, either 0 or 1, and if the choice is 0, basically it creates a negative entangled state. 1, if the choice is 1, it will create a positive entangled state. Now again, if there is a positive entangled state, I am passing the qubit to get a value positive, that is to get the value 1 and not 0. And likewise, if the choice is 0, that is to prepare a negative entangled state, the negative entangled state will collapse into a negative qubit, that is the value 0. Okay, so let's just run it. Yeah, so my all three operations have successfully been rendered. Now what I have to do is again create a function to pass any random qubit to this entire this prepare random message operation, right? So for that, let's write. First of all, I'll be needing diagnostic files, Microsoft dot quantum dot diagnostics, in order to take the all the basic qubit values and to ensure that they are passed through the quantum algorithm. And the next library that I have to use, I think it's what it is called, Microsoft dot quantum dot measurement. Yes, definitely I have to measure finally. It is 0 or 1, right? Okay, so the libraries have been used. Okay, now yeah, using the q as a qubit, this qubit keyword will give me any random qubit using this above diagnosis library. And using this qubit, oh sorry, I just forgot to define an operation random measurement, and no will be passed. And yes, this time I want a result to be printed out, so that's why I'll be writing result here. And cool. Okay, so now we go. Yeah, so using a q as the random qubit, let's just keep it set plus, right? And pass the q operator. Now when I set plus to and pass this qubit, what it basically does, it will directly go to set plus, but via it will choose this operation, because this operation will then only sorry, this prepare random message is the only operation that triggers the set plus or set minus, right? So even if I write this set plus operation directly, it will go to this prepare random message, pass the qubit, check whether it needs to be negatively check whether it needs to be measured negatively or measured positively, and based on that it will forward it to either set minus or set plus. So yes, you can say that it's a kind of overriding, because even if I am writing set plus here, it will not directly go to set plus operation. Instead it will go to prepare random message, because that's the only way that I'm triggering both operations. Okay, so yeah, let's say that I'm as of now I want 1 as an output, so set plus, and I have passed the q as our qubit. And what I wanted to return is a reset, right? A reset or an h Pauli get. But as you have seen that I have already used the h gate here, what I wanted to do now is measure, right? So measure, reset it 0 or 1, that is the rational number z, and pass the qubit. Set plus, why is this getting, oh sorry, the number, it's just smaller. Great, so the random measurement is successfully created. Now I'll actually simulate this algorithm, random measurement, and so that's 1, right? You can see that I have the output of my random qubit as 1. Now let's just flip it, it's again 1. It has to change sometime, but it's not changing as of now. And yeah, so it's 0, you can see, right? The random state has again been 0, but you can see that I have called set plus here. What set plus basically will do, it will return the value 1. Then how come it comes 0? Only because even if I mention set plus here, it will basically first go to prepare random message, because that is the only way either set minus or set plus operations are triggered. That's why it will have to always go through the prepare random message operation and then go for the next manipulations. Yes, so we're done with our first quantum programming, and let's just get back to PPT and our session. Okay, so with that, yes, the applications. Okay, so quantum simulation, as you already know, this photosynthesis, not my cup of tea. Cryptography, yes, of course. Let's talk about that. Mathematical algorithms used for cryptography, the model algorithms like the AES 128, RS 2048, ECDSA 256 are not susceptible to brute force attack, right? Because even if we want to go for brute force attack and actually crack the encrypted message, it would take years, and even years as in billion trillion years of years, in order to decode what the actual information is trying to say. However, it is possible to create a unique algorithm for quantum computers, and one of the great example is, as I mentioned it here, let me grab a pen. Shor's algorithm. Shor's algorithm is basically a way through which you can use quantum computers, exploit the properties of quantum mechanics, and actually decrypt the entire message. Yeah, so what Shor's algorithm basically does is it drastically reduces the processing time required in order to generate the random strings that fits the entire sequence of the encoded message. Classical computer, on the other hand, does take an exponential time. So yeah. On the other side, symmetric algorithms used for encryption like AES are still thought to be safe because they have a sufficient length of 256 bits, right? And other asymmetric operations like RSA and ECDSA are essentially one of the things that our classical computers cannot solve it in any kind of polynomial time. I mean, it can solve in polynomial time, but it will take trillion years of years in order to actually decrypt what's the value in worst case, right? Okay, so cryptography, the quantum cryptography here comes into picture, and using that we can actually correct what's the original message was in polynomial time, and that too, let's say there is a let's just say that there is my name, the message name Jay, right? And I'm using the AES standards encryption in order to encode my message. So there will be a 256 bit string, long, that when used the symmetric key by AES, you can decipher it and get the value J, right? But since I don't know the value, I have the only option on classical computer to brute force. What if I have an quantum computer? If you use the Shor's algorithm and pass this AES 256 bit key, this encoded message, in polynomial time within, I don't know, within a couple of minutes, this entire 256 bit long string will be then deciphered into just J. So that is how quantum cryptography works. I won't get into much detail because we are already late in our time. Okay, so furthermore, yes, the optimization problem exists in almost every industries and business functions, and some of these things really much long time and on traditional computers. So the optimization technique, the quantum optimization, basically functions on two of the properties: quantum annealing and of course the quantum computer, the universal quantum computer. quantum annealing again is an optimization method that is expected to surpass the classical computers in terms of optimization problems. It's a method used to find the optimal solution of problems involving large number of solutions. Like, let's say I have a great number, a very big number, and I want to divide it into long prime numbers. So using Shor's algorithm, we can do it. Sorry, not the Shor's algorithm. Using the what was that fractional method? I think, yeah, that's what the Shor algorithm only. Yes, Shor algorithm always also has the capability of dividing this big of number into subsequent prime numbers that, when multiplied again, will result into the original number. Next, finally, quantum machine learning. Quantum machine learning is basically based on two principles. One is the quantum data, and another is the quantum model. Quantum data is any data source that occurs in any kind of natural or artificial quantum system. Let's say we have Google Sycamore computer, and that Sycamore computer is generating a pair of qubits on its own. The quantum machine learning model doesn't know that these are the qubits, and I have to manipulate them. So the quantum data is the term used to convert these qubits into understandable forms that machine learning accepts and process it through the entire algorithm in order to generate the inferences. And finally, this another term, quantum model, can represent and generalize the data with quantum mechanical origins. That is, by using the principles of quantum mechanics stated earlier, like quantum entanglement, quantum tunneling as well, and all. Of course, using this Pauli's measurement firstly. Yeah, so you can see that we are not using the actual quantum computing here. The stage where today's world reside in is the NISQ era. NISQ stands for noisy intermediate scale qubits. You can say that this NISQ qubits actually pretend to be the pure qubits, but are not actually, right? So as I mentioned, there will be a slight probability that the entangled state collapse into 0 with a 99.999% probability, and into 1 with 0.0001% probability. But as I said, that you have to always make sure that it's either 100% or 0%. For that reason, the quantum machine learning models are hard to diagnose and even construct, because the drawbacks that we are currently facing in the NISQ era are too hard to be solved. And once this NISQ era is passed on and we are able to actually simulate with either 100% or 0% accuracy, we will be good to go for the incorporation of all the models, whether it's machine learning, whether it's optimization, whether it's any other simulation. We are good to go for getting 100% accuracy from this method. So yes, that's what actually the quantum computing is. And yeah, that's it for our session. So yeah, cool, we're good to go. Any kind of queries, most welcome if you have. Else
Rugved
we
here.
conclude here. Hello, yes.
Hello, Rugved here. One of the main questions I wanted to ask is, hello.
Yes, yes, I
I
am
think
hearing.
someone else is asking a question. Hello.
Sorry.
Okay, my question was that is Q-sharp actually workable on an actual quantum computer, or is it just used for simulation?
Q-sharp is actually used for simulations and not for quantum computer. I mean, if you have quantum computer, why do you need any kind of language or API in order to construct? You can just pass the instructions in the, I don't know what is the form, but it's definitely not the Q-sharp. If you have Microsoft's quantum computer, you need to have its own set of instructions you can pass, and Q-sharp is definitely not the language. It's just made for simulating the quantum purposes.
I think it will be best if we ask the question in the conversation section. Thank you.
Okay, so if you have any kind of questions, always feel free to ask me out. You can always find me at LinkedIn. My name is Jairang on GitHub as well. And yeah, so that's it from our guys. Have a nice day. Goodbye.
Hello. Hi. Hello. Hi.
Guys.
Hello. Hi.
Okay, it was nice to meet you guys.
Guys,